liquid into this, and you want to fill this up, and so that you have a filled corner in this way. Okay, filled corner in this way. Obviously, this is a symmetry line, so I'm just going to consider half the corner. Okay, and basically, this is solid. This is also solid. And this is at 90 degrees. Okay, so this is exactly something like this, and you're trying to fill the corner here. Okay, so this would be approximately, this would be 45 degrees. This would be 45 degrees. Okay, and obviously, as you fill it up, the main thing, if you want to fill anything, you need to make sure that the energy is minimized. Otherwise, the water will not live there; it will just come off. Okay, so it will just come off. So basically, let's say that if we have this is an area of delta A. Okay, so ये भी delta A है. This is also delta A. Okay, and basically, if this is delta A, and say that if you want to fill it up, if you want to fill this up, this would be something like delta A sine 45 degrees. Okay, this is the area projection there. And what we are looking at is this guy, this is liquid. Okay, so this has a surface tension of sigma LV. Okay, this has a surface tension of sigma LV. So one way to look at is the surface energy of this as projected onto the surface. So it has to touch the surface, it has to fill the surface. So if you project this surface energy onto the surface, then on the surface delta A, on this surface, you can say that the surface energy is going to be sigma LV delta A, that is joule per meter squared times meter squared, so joule sine 45. So there is the surface energy imposed by surface energy LV on one of the arms, so on one arm of the corner. Okay, obviously there are two corners, but we are just looking at one because there is symmetry here. Okay, obviously the other thing is you have on this particular surface. So if I zoom this in, this is your wall. The wall has a surface energy, this is filled by liquid, so this is sigma LS, okay, and basically the surface energy here would be sigma LS times delta A, because the area is delta A, okay, and this is 45 degrees. The surface energy here is sigma LV delta A sine 45, okay. So if you want to fill this corner, the minimum condition for filling the corner, so if the corner was completely empty, so if it was not filled, so this is a corner and it's not filled, the surface energy here is sigma SV. Okay, this is solid vapor surface energy when this is an empty corner. Okay, so the minimum condition for filling this corner, say half a corner, I'm just looking at the half aspect, would be basically sigma SV times delta A must be, so if you want to fill the corner, the net energy driven by the liquid phase, liquid vapor or liquid solid, should be smaller than the SV delta A, than this solid vapor energy. So this should be greater than sigma LV delta A sine 45 plus sigma LS delta A. Okay, so this is the minimum condition. Okay, if sigma SV is smaller than this, if the net energy imposed by liquid vapor surface tension and the liquid solid surface tension is greater than the solid vapor surface tension, it won't fill the corner. It won't fill the corner at all. Okay, so what we can do is, if we just look at this, it's a very simple exercise next. So I'm just going to go next page. So this would be just to repeat, sigma SV is greater than sigma SL plus sigma LV sine 45. Okay? And you also know that, say that obviously any liquid, when it is trying to fill, it will have its equilibrium contact angle. So if you use the if you use a Young-Laplace equation, cos theta E, some equilibrium contact angle will be sigma SV minus sigma SL divided by sigma LV. Okay, sigma LV. So from here you will get sigma SV minus sigma SL equal to sigma LV cos theta E. So I'm going to substitute this here. So this implies, if I bring this to the other side, sigma SV minus sigma SL, so this becomes sigma LV cos theta E should be greater than sigma LV, sorry, yeah, sigma SV minus sigma SL is that, okay. Yeah, so sigma LV sine 45, okay. Okay, so this becomes the condition to make sure that you have you can fill up the corner is that the cos of contact angle, cos of the equilibrium contact angle must be greater than sine 45 degrees. Or in general, if you have a corner of any angle, say phi, then I would say the cos of equilibrium contact angle should be greater than sine phi by 2. So this is the general condition for filling up the corner. Okay, this is a general condition. So, and I think this is a very interesting thing. So especially when you design surfaces and you want, say that if you want to have a Wenzel structure and you want, if you have this patterning in such a way that you've got these poles and you've got this, obviously it forms a corner and you don't want to fill it. You don't want to fill it. You don't want to have a Wenzel state. So if you can probably, just by energy analysis, if you are satisfying these conditions, there's a good chance that you will not fill it. Okay, so that can be taken into account in terms of the design as well. Okay, so this was just the kind of a sojourn into just a recap of what we were doing yesterday and just doing a simple energy analysis to understand the effect of contact angles and probably some impact on design as well. Okay, so with this, what I will do is I'll just go back to, as I mentioned, I'm going to shift gear. So one of the things I did mention to you is that when we look at these systems, it's not just enough to look at experiments. It's not just enough to look at modeling. It's not just enough to look at just theory. So in the next few days, what we're going to look at is we're going to look at 3 arms of the methods that we're going to use. So if you take a triangle, the way we study fluid mechanics nowadays is you obviously do a lot of theory. Okay. You do a lot of DNS, okay, and then you do a lot of experiment, and you combine all of these things together to actually get some analysis. And obviously, the fancy word for combining all of these things together is called as machine learning. But ultimately, it's the same thing. So I've been doing that for a long period of time. So today, what we're going to focus on is two different ways where theory can give you a lot of insight into your droplets or a pool problem. Okay, so there are 2 methods which we're going to talk about. One is called as the stability analysis. Okay, it talks about it's very different. Stability analysis, it doesn't give you answers. It doesn't give you numerical values. No, it tells you whether your system is stable or unstable or neutral. It does not tell you anything else. If it is unstable, it tells you the growth rate of perturbations, how fast it becomes unstable. It does not give you answers, okay, this is the contact angle you need to work on. No, it doesn't tell you. It just tells you the state of your system. Okay? There is another method. The other method which we're going to use is lubrication. Okay? Lubrication theory gives you some answers. It gives you the film thickness, it gives you the height of the droplet, it gives you the evaporation rates, it tells you everything. It gives you answers. But all of these are subject are subject to assumptions. Okay? Are subject to assumptions. And we need to be very careful, and we need to give these assumptions a lot of respect. Because in some cases, the assumptions are valid, but the experiments might show that they're actually not valid. Okay? So we may have to relax those assumptions and things like that. So today I'm going to talk a bit about, and also another disclaimer I should make here, is when we do stability analysis, it's not, I can't do a full stability calculation or a stability derivation in 1 hour. It would take about 1 week for me to do a full stability analysis for one case. So today what I'm going to do is I'm just going to give you the steps or the key message, how a stability analysis is done. I will also be talking to you about a key message, how lubrication analysis is done. From tomorrow, I'm going to show you examples how these can be combined. Okay? I'm not expecting you to derive it because it's going to take a lot of time. But I'm going to show you how they can give you a lot of insight. Okay? So very quickly, so if you want to go into, so what is stability? The universe is unstable. Okay? The universe is always going towards the state of maximum entropy. Okay? So flows as well are highly dynamic. So there's no such thing as steady flow. Okay? So I think this is my biggest complaint when you look at any CFD software, commercial, ANSYS, whatever, Fluent, whatever you will see. The first example they will give you is two-dimensional flow, turbulent flow. There's no such thing like that at steady state. It's not possible. Turbulence is never steady. Turbulence, the very reason turbulence is difficult to study is because it is highly unsteady. Okay? Even if you have a laminar flow, supposed laminar flow, it's a dynamic thing. It always moves. Okay? So there's no such thing as a stable flow. Okay? When we say that the flow is stable, we just mean that it has, okay, the flow rate is constant, it's not very disturbing, you don't have any kind of major fluctuations going on. That's what we want to say. So in general, when we say a steady state in flow, it means that it has a constant dynamic condition. And that dynamic condition, there's no acceleration, there's no deceleration and all that. That's what we mean. Okay? Now, the thing is, all flows are unstable. And all these flows, the reason they are unstable is because there are some inherent instabilities. Okay? Typically, the most important instability that happens even without our notice is the surface roughness. Okay? Is the surface roughness. The surface roughness causes something called as a Tolmine-Schlichting instability. I'm going to show you. So basically, if you look at any roughness, so the roughness, if I exaggerate it, it looks something like this. So you've got flow on top of it. So basically, if I plot a velocity profile, it might be like this. But then as it negotiates through the roughness, this guy has to twist and turn in all these fashions. And as it twists and turns, it's going to create these eddies. It's going to create these eddies. These eddies, if they are strong enough, they will start affecting the entire flow. That's when you have turbulence, incipience of transition flow or turbulent flow. If your flow rate is not strong enough, these guys will die because of viscosity. Okay? These guys will slowly die down and they won't affect the entire flow. That is when you have a laminar flow. Okay? So this particular instability, which is given by shear, which is driven totally by del U by del Z, this is called as the Tolmine-Schlichting instability. And it is a fundamental instability in flow. Any flow will have it. In most laminar flow, in your microfluidic devices, Tolmine-Schlichting instability is too small, so we ignore it. Because it is not creating turbulence. But then, if you have a larger system, if you want to construct a smoothish pipe, this is what is going to play a role. If you want to have a very smooth pipe, in fact, in Manchester, people have created a smooth pipe which shows laminar flow of Reynolds number of 6,000. Okay? That is an ultra smooth pipe. Obviously, practically, we don't want to make it. We don't need to make it because everything has roughness. Okay? So basically, when you have so all flows are subject to instabilities, and If you look at any multi-phase flow, so basically if you have liquid and a gas, both of them flowing in a pipe, the gas will have obviously some sort of a Tolma-Schlichting instability. It will have its own instability. The liquid will have its own Tolma-Schlichting instability. But then there is also this guy sitting in between, that is the interface driven by surface tension. So obviously any sort of a multi-phase flow, when both gas and liquid are moving, they are subject to three instabilities. One is the shear instability in the gas phase, the shear instability in the liquid phase, and the interfacial instability here. Okay? That's why you have waves in flow. If you have a completely stratified system, if you look at a flow probably at low flow rates, low gas and liquid flow rates, you might find that the interface might be having slump disturbances, but ultimately is nearly straight. It just means that instabilities are not very strong. But as you increase your gas flow rate, or as you increase your liquid flow rate, you'll see waves developing on the interface. Not because of the bulk mode in the gas phase or bulk mode in the liquid phase, it is the interfacial, it's the surface tension which is playing a role here. Okay? And the surface tension is basically because if I plot the velocity fields here, it looks something like this. So it's basically a viscosity contrast between the two. The more you have the viscosity contrast between the two, the stronger is the instability. That is the interfacial instability. Okay? This is called as the Yi mode. Okay? I'm going to show you many other examples. Okay? So basically all flows are driven by disturbances. All multi-phase flows are driven by disturbances. And in fact, the ultimate state of the design of your multi-phase system is dependent totally on the instability. Okay? If you have a churn flow, it's a combination of interfacial instabilities and other bulk instabilities coming together forming these complex systems, complex flows. Okay? So it's very important for us to really understand these flows, understand the instability in great depth. So ultimately, what's the point in knowing this instability? So if you want to design, say, an oil and gas pipeline, and you want to make sure that the flow is as stratified as possible, it has an advantage because that means it's low pressure drop. Okay? So what people do is they pump in all kinds of surfactants to make sure that the interfaces, or suppressants to make sure that the interface is as flat as possible. Okay? To help that. Because once you have waves, it can go into slug flows, which is like a tsunami in a pipe, and which has huge pressure drop and pressure drop costs to it. Okay? So you need to understand these instabilities well and how they impact engineering systems. So one of the things I would like to also indicate is basically that when people say that my system is laminar, normally I never believe it, because there's no such thing as laminar flow. It's basically a figment of imagination, most of us case, and it's basically a laminar flow is an assumption we make to make our flows simple, so that we can easily calculate them. Okay? So laminar flows, yes, in microfluidics they do exist. If you have a high viscous system, they do exist, that's fine. But they're so small, but usually if you have such an organized flow, it's an exception to the rule of fluid motion. Okay? So as I mentioned, stability analysis gives you more about the expected dynamic state of the system. Okay? Where your system might lead to. Okay? It doesn't give you an answer. It doesn't give you a numerical answer. So what happens? So typically, as I mentioned, you will have initially, you have this is an example I always cite because it's a very more accessible example to everyone. So you've got the gas liquid flow here. So as you start off your flow, you probably will have tiny waves coming up. Okay? Tiny waves coming up. And what at this point we say is that it's a very early stage of growth. And all of these waves are typically starting off with their amplitude even in submicron remit. Okay? So typically when you have a stability analysis, we consider the growth of the smallest disturbance to a large value. Okay? So typically, or if you want to see the growth of a tsunami, it starts from probably around a micron size disturbance to kilometer size. Okay, that and that is completely driven by the energy of the system. Okay, of tectonic motion. So obviously you start from a very small wave here. So here you can say that you are still a sinusoidal wave. Okay, but as time grows, it will show a completely different feature. As time grows, this grows in this way, still sinusoidal, but after some point it becomes like this, not sinusoidal, and at some point it becomes a slug. Okay, so this is what we call, this is at later times. So at early times, we can say that the disturbance is still a bit sinusoidal. Okay, and usually when we do stability analysis, we look at the early growth, because the way, if you understand how your waves grow in early stages, you can predict what is happening at the later stages. Okay, so early growth, this is called as a linear stability analysis. And the same thing we can do, this is an example from our Langmuir paper. So this is where a droplet is evaporating. This is an ethanol droplet, which is evaporating on a copper plate. And what they're showing is basically an IR camera. So obviously IR, it will show the temperature feature all along the interface. And you can see these spokes coming off. Okay, these are called as so-called thermocapillary instabilities or hydrothermal waves. And what we find is that these guys actually turn around. They can go clockwise or they can go anti-clockwise. And what they do is they completely change your heat transfer characteristics. So if you want to, in most cases, they enhance evaporation. If you suppress these instabilities, you will slow down the evaporation. Okay, because it's almost like an internal convection current that is happening. So Prandtl number. So it's basically Prandtl number and the ratio between Prandtl number and the surface Marangoni index. Okay, so it's completely based on it's a surface tension, it's a hydrothermal instability, completely dependent upon the Marangoni number as well as the Prandtl number of the system. So you can see that in methanol droplets. I'm going to show you more examples later on. So when we do a small linear stability analysis, we also see these features coming up. Okay, these are not numbers here. They're just showing where are the waves appearing. That's it, and what is the feature of these waves. So that's what a stability analysis gives you. That initially this is your temperature profile, and you can see as you plot your temperature profile, you can see these spokes coming up. Okay, which is not exactly similar, but at least it represents what is happening here. Okay, so stability analysis will give you that, okay, this system is unstable. How long will it be unstable? How long can it, obviously when you have an evaporating droplet, you change the shape of the interface. Sometimes you will find that at certain shapes you don't have any instabilities. It is almost empty, there's no hydrothermal waves. In some cases they come back again. Okay, so there's also a shape dependence there. Okay, so these things are best studied using a linear stability analysis. Now, if you consider late times is pretty difficult to understand by linear stability analysis. Normally, there's something called as a nonlinear stability analysis, but we don't do that. It's quite unnecessary. Okay, so this is what you have these waves which are developing into huge structures. Okay, and typically we study them using DNS. Okay, we study them using DNS. If you look at these droplets, you can see that initially this was just a deposited droplet here. It showed as it evaporates, but then in another system, you could see the droplet completely spreads. It forms these fingers, and you've got these nonlinear structures appearing there, just before it evaporates completely. Okay, so these are best studied using DNS. So basically, linear stability analysis is very good, especially to understand the initial states of your system. Okay, the initial states or what your system can do. So what are the different types of what do you find in nature? Okay, what are the different types of waves? Okay, the first thing is, this is very common. It's the Kelvin-Helmholtz instability. Okay, so you can see these clouds. So you have these clouds which are cat-eyed shape, and this is completely driven by above the cloud, the velocity of air is bigger than the velocity below. So it's the same viscosity region. So the viscosity is not different, the density is not different, it's just competition between two velocities, which is creating these cat-eyed fashions. Okay? So this is the Kelvin-Helmholtz instability. We can see that within under oceans as well. So if you have different ocean currents going at different velocities, in some cases you will find these rolls within the oceans. Okay? The other thing is, the one which I mentioned is because of viscosity contrast. So this is where you have a gas and a liquid, okay, and you've got this velocity contrast between the two, and also you've got, most importantly, you've got a viscosity contrast between the two. You'll also have density contrast, but viscosity contrast is the one which drives the interfacial instability, okay, leading to ligaments and other things, and so on and so forth. Okay. The other thing is, obviously, we talked about the Tolman-Schlichting mode, which is internal. So these are these Tolman-Schlichting waves which disturb the boundary layer. Okay, I don't need to go too much into that. The other thing is basically different ways in which instabilities can kick off. So if you have a two-layer system, if you have gas and liquid flowing through, sometimes you have another instability which is kicking off from the wall. It's called as the Miles instability. So Miles instability is kicking off more towards the interface, but not exactly on the interface, but close to the interface. Okay, that is basically, it's like a forcing it's like a pressure forcing which the interface feels very close to the interface, and that's how a Miles instability develops. There is also another mechanism called as Phillips mechanism, by which you have direct forcing by turbulence. Turbulence itself indicates these pressure pulses, okay, and that can also come up. Okay, so obviously the examples which I showed, the pictures which I showed, they were 2D, but you will also have 3D instabilities. So whenever you have a wave, you can have a wave which is growing at the same time, but this will develop a tongue, but this won't develop a tongue. Okay, so you can have a three-dimensional instability as well, which is occurring. Okay. So what do we do? So one of the things we also look at is how do these waves propagate. Now, if you hold a rope towards one side, if I hold a rope towards one side, I can just give a pulse and the wave travels. So the instability is traveling only in one direction. That is a convective instability that is pushed by, if there's a flow, that will be pushed by that. But in some cases, if you are a chemical engineer, you would probably know the condition of flooding. So typically, if you have a distillation column, so you've got a liquid which is actually flowing down in this way, and you've got a gas which is going up. Okay, so this is usually used in absorption and distillation columns. So what would happen is, because of the interaction between the two, there are waves which are developed. Okay, but the gas is going in the opposite way than the liquid. If you keep increasing your gas flow rate, at some point, while the actual mass of the liquid is going down and the actual mass of the gas is flowing up, some of these waves actually become a standing wave. It's just this balance between surface tension and inertia and gravity, standing wave. This point is called as loading condition. Okay? Now, if you keep increasing your gas flow rate, the waves then travel upwards. That is called as the flooding condition. Okay? And so in the flooding condition, the waves are traveling opposite to the direction of the liquid. So this is where the waves actually start growing against the flow. They go all over the flow and flood the entire domain. And that's when your column becomes inoperational. Okay? So typically when you're operating a distillation column, there is a limit. So if you have bigger gas flow rates, you have an advantage of big waves, give more mass transfer and heat transfer, but then that's a limit. The limit is the flooding point. Okay? So this flooding point is basically is something called as an absolute instability. So in an absolute instability, in a convective instability, the wave only goes in one direction. Okay? But in an absolute instability, the wave goes in both directions. It goes opposite to the flow, it also goes with the flow. It goes in one way. So in those cases, you can imagine when your column is flooded, you've got waves, the whole column is completely flooded with water, with liquid, and it becomes inoperational. Okay? So this is what is the type of instability that can happen, okay, or the character of the instability. So whether your system is convective or absolute, That's an important thing which people look at, especially when designing these systems. The other thing which people look at is when you have, so if you, I talked about three-dimensional waves. So if you look at a three-dimensional wave, you got a wave which is two-dimensional, and in a three-dimensional wave, you may have a different kind of a feature which is looking like this. Okay? Now, if you have this, what it means is that there are different waves which are competing with each other. Okay? There are different waves, there are different wavelengths which are competing with each other. And this calls for a different analysis. It's called as the linear transient growth. It's called as a transient growth analysis, where you compare the competition between different waves. And then you can actually predict which is the wave in your system which is going to pull you the whole thing, or which is the wave which is important for you. Okay? And then you can design your system in that way. So that is usually used in this transient growth analysis. So as we mentioned, I mean, you obviously will have, when you consider stability of two systems, this is a very simple, this is a very standard example where you have the system, the geometry of the system doesn't change. You've got a pipeline, gas on the top, liquid below, whatever, okay? And this is going to remain as it is. The geometry of the system does not change with time. It's the flow which is changing and it's showing its shape. So this is a system which has a constant base state. Or we can say that you can have a very simple, if you take a Navier-Stokes equation, you can cut down the del by del t terms and you can get some sort of a steady state. Okay? Apparent steady state, because things are not changing much. Okay? But there are other systems where you don't have a steady state, you don't have a base state, especially when you have phase change. So if you have a droplet which is evaporating, you start with a height h, finally it becomes h1, h2. So the dynamics of the system is completely dependent on geometry. So the geometry of the system changes. So these are the flows where your system has no base state. You can start, you have an initial state, but that's not the base state. You have an initial state that remains for a few seconds, that remains for an instant of time, and then it keeps changing. Okay? So typically when we have a base state, doing a stability analysis is easy. When you don't have a base state, it becomes a bit of a challenge, because you don't know where to start from. Okay? I'm going to explain things. You also have the same problem when you have reactions in the system. Okay, because reactions are dynamic, so there's no such thing as a steady state reaction. So how do we normally do this? So when we consider any base state, when we consider any state of a system, so this is like at time t equal to 0, this is the state of the system and the waves are looking like this. Okay, this is, say that this is at time t equal to 0, the waves are looking like this. What we're going to do is we're just going to put a small disturbance on top of it. Okay, so let's give it a small wiggle. Okay, so give it a small disturbance. And typically, when you have a disturbance, any disturbance can be represented in a Gauss form, and it will have a cos component, it will have a sine component, and typically it's a complex perturbation. One of the things I should tell you is both the real part and the complex part have a huge role to play. Okay, if you look at this term, alpha and beta, this shows how the system grows with space. Okay? So it's not just growing with time. Your perturbation can grow as it passes through the system, because it is traveling it's traveling through a length. So it is growth rate with respect to, it's a spatial growth rate. But at the same time, you also have the time component here. So that is basically, it grows with time. So your waves grow not only spatially, but also temporally. Okay, so we look at both these aspects. Okay, we look at both these aspects. Actually, the real growth rate gives you the wave numbers, that is the most unstable mode, and the imaginary one gives you the most dangerous frequency. What is the frequency at which your waves would be most active? Okay, so both the real part and the imaginary part give you a lot of information there. Okay, what we then do is, if you have a steady state, we substitute this in the steady state and we linearize the governing equation. So essentially, you start with Navier-Stokes equations, you add this disturbance onto the Navier-Stokes equations, and then you just take the linear terms. you ignore the nonlinear terms. That gives you something called as the Or-Sommerfeld equations. Okay? And again, as I mentioned, it won't give you any answer. It tells you whether your system is stable or unstable. That's it. And the way it tells you is gives you it's an eigenvalue problem. It tells you the growth rate. It tells you the growth rate with respect to some wavelength. Okay, this is the growth rate with respect to wavelength. And what it will give you is, it will give you, when you solve these equations, it will give you how growth rate changes with respect to wavelength, or this is the wave number. So essentially what it means is it spans across infinite number of waves, and then it tells you that, okay, if I go from the lowest wave number to a certain wave number, this is the region of wavelengths where the system is unstable because the growth rate is positive. When it crosses the zero line, this is where the growth rate is neutral. It neither grows nor it decays. Okay? So the wave remains as it is. Okay? This is the range. If your system is operating in these wavelengths, you will have a stable system. You won't have an instability at all. Okay? So in most cases, in most engineering systems, you are in an unstable system. It gives you a lot of advantage. It gives you a lot of heat transfer because you've got waves, you've got more surface area, you've got this and that. So essentially, you can then decide on where you want to fix your disturbances in. So you can allow for disturbances, but you can suppress these ones completely. Okay? So you maximize the efficiency of your system. Okay? So this is where you're the most unstable. Okay? So a stability analysis gives you the zone of stability for any system. It does not give you an answer. It tells you how your design is performing and under what range it will give you, at what type of instabilities it might give you, or it may not give you anything. Okay? It tells that to you. Okay? And then you can decide on whether your design is good enough for you or not. Okay? But again, this is from the initial stages of wave growth. And these are very important because the initial stages are the ones which decide on the final state of the system. Okay? So that's a very important thing. So basically a stability analysis, this is the general method. As I mentioned, I'm not going to be deriving things for you here and all that because it'll take like 2 more weeks to do that. Okay? So what we can do is, just to summarize, so when we look at any system, what we do is we take a supposed steady state and then you give a perturbation. If the perturbation grows, you're in an unstable system. If the perturbation does not grow, the waves will remain as it is. Jo waves aapne diya, they'll just remain like that. If the system is stable, that means that the waves will decay. Okay? So it will suppress any sort of an instability in your system. Okay? That's what happens in so-called laminar flow. So at low Reynolds numbers, you don't have enough kinetic energy to drive these waves. Everything gets dissipated to viscosity. Okay? So that's why you can have when you have in microfluidics, you will not have much of a turbulence case. So that is giving you the information in the state of the system. Now what we're going to do is we're going to look at another method which we use for droplets. It's called lubrication theory. Okay? And in lubrication theory, it's an important thing to understand where we can use it. Lubrication theory is a very, very special theory. It is applicable, so if you have it is applicable for flow domains which have very small height with respect to length. So H is much, much smaller than L. Okay? It's a very thin film. It's a very thin film. So that when you're using lubricants form a very thin film. So if you look at the thickness of the lubricant with respect to the surface it is coating, it's a very small thing. So if I can define some kind of a parameter called as epsilon. This is called the shallow water parameter or lubrication parameter, H by L, which is very close to 0. Or I would say very, very much less than 1. Okay? So you can define this as a shallow water parameter there. Now, what engineering systems can do that? Obviously, you can have droplets or puddles. So where your droplet is very shallow, so you can have a probably contact angle of less than 30 degrees. To contact angle of less than 30 degrees, you can have a very shallow droplet. Obviously, films. The puddle problem that we talked about yesterday. This is obviously another place where you have a falling film. So you can have a falling film. And we use falling films in heat transfer all the time. This is another common example. This example is a boundary layer. So typically, when you in turbulence, if you've done boundary layer theory, boundary layers are basically lubrication layers. We can use lubrication theory there. Because boundary layer is very thin, is probably to the order of microns or probably less than that, or probably slightly more than that, tens of microns or something, in comparison to the size of the domain. Okay? So that's where you can use lubrication theory. Okay? I'm going to give you a small example of how it can be implemented. Okay? So this is where I'm going to look at. And one of the examples I'm going to show you is boundary layers. I'm going to show you some more examples tomorrow on droplets and things like that, but this is a more accessible example. So what we have is you've got a surface where you've got a weird surface. This could be a kind of a helmet, okay? And you have got this airflow on top of the helmet, and what you're trying to predict is the length of the boundary layer or the height of the boundary layer, okay? So when you look at this, you would say that it's almost 2D, because essentially the boundary layer thickness is so thin. You've got this wall which is like this, and the boundary layer which is very thin and very close to that wall, okay? And typically the boundary layer thickness is given by delta naught. Okay, it's an approximate. So this is how your boundary layer is in comparison to that. So one thing we quickly say is delta 0 by L, if L is the length scale of the wall, is much smaller than 1. Okay, much smaller than 1. Okay, so obviously if you consider this region, it's almost looking 2D. Yeah, boundary layers also have 3D features, but if you look at it from that perspective, they are essentially 2D. So because they are 2D, I can actually use a 2D equation here. Okay, so you will have a wall, you will have a very thin boundary layer, and this is, so one of the important things about the boundary layer is all the action happens within the boundary layer. Okay, so you'll have a velocity profile which looks like this. So this is the region where you have u and v. Over here, it is only one-dimensional u. Okay, this is where you will have u velocity. This is where you will have v velocity. But beyond the boundary layer, you just have mainly the free stream velocity. Okay, so all the action actually happens here, and this is the area where your viscosity is most felt as well. Okay, so if you look at this, so we have a simple continuity equation, del u by del x plus del v by del y. Now the thing is, and because it's a 2D system, we can have a 2D momentum equation as well. Okay, so this is your boundary layer. This is my y-axis. This is my x-axis. And u and v are in action over here. This is how your velocity profile looks like. And because it's such a thin thing, we are not even considering the effective gravity is almost 0, because it's such a thin film. Okay, so we don't have rho g term here. We don't have rho g term here. So one way to quickly look at how do we reduce the system into lubrication equations. So obviously, till now we have just dealt with Navier-Stokes. They're full Navier-Stokes. They are not reduced to lubrication approximations at all. One way to look at is do something look at the length scales. So obviously, what we have done is this particular length scale is delta naught. This particular length scale is L. So length scale in X is the free stream is the body size, that is L. Length scale in Y is delta naught, and delta naught by L is much less than 1. Okay, so you will have and consider that you have an approach velocity of u infinity, whatever. This is your velocity on top of it, and the idea is that we want to understand what is happening here. Okay, so this is your average boundary layer thickness, delta naught. Okay. So very, very simply, again, what we can do is we are quickly seeing. So if your x length scale is L, if your y length scale is delta naught, okay, the velocity in the x direction, is governed by u infinity. That is where your direction is. There is something, the v velocity in the boundary layer is something which we don't know. Okay, this is the v velocity within the boundary layer. So essentially, you have this boundary layer here. This is where you have u and v, and we have no idea what v is. We have some idea what u is. U is more as a function of u infinity. We are not terribly worried about that. Okay, but something clearly we are not aware is v. So what we can do is we can do something called as an order of magnitude analysis. So we can say that this one, del u by del x, is something of the order u infinity by L. U corresponding to u infinity, x corresponding to L, is equal to, I don't know what order of velocity v is, divided by delta naught. Y is similar to delta naught. Okay? So if you do this, because there is an equal to sign here, I can write this as order u infinity by L is approximately equal to order v by delta naught. Approximately equal to. So therefore, from here I can get v is something like delta naught by L u infinity. And this is an order of magnitude. Okay? So this is just an order of magnitude analysis with respect to understanding what v is. Okay? And then what we can do is we can do the same kind of an approximation. We can do the same kind of an approximation with our x equation and v equation. I'm going to show the y equation. So if you look at this, you will have u del u by del x. U del u by del x can be written as something, its order again. U infinity, this is u, therefore it could be u infinity. This is del u by del x. So this is u infinity by L. So this is u infinity squared by L. If you look at v, so v can be written as order v del u by del y. So this is u infinity by delta naught. We can substitute what is v from your continuity equation. So from here, I'm going to get order delta naught by L u infinity by delta naught. So you can see that you would simply get u infinity squared by L on both sides. So this is u infinity squared by L. This is also u infinity squared by L. And which is great because at least we know that we are in the right way. Okay? So both of these terms have got the same magnitude of strength. Okay? Same magnitude of strength. Something which we can't tell is, I don't know what the value for pressure is, so I'm just leaving it like that. But here what we are looking at is order of magnitude. So we know that the left hand side must be balanced with the right hand side. Okay? So if you look at again these terms, if you look at del u by del x squared, this is u by L squared. This is basically del to u by infinity is u infinity by del naught squared. L squared is, L is much larger than delta, so therefore L squared is much larger than delta naught squared. So that means u infinity by L squared is approximately 0. Okay? L is a big quantity, L squared is far bigger quantity, 1 over L squared is far smaller. In other sense, on the other hand, if you look at delta naught squared is terribly small. Delta naught squared is even smaller. 1 over delta naught squared is huge. So this guy will remain. Okay? So if you look at the balance between these two sides, you will get something like order of u infinity squared by L, this is the this is the left hand side, is equal to order u infinity by delta naught squared. Okay? And if you just and obviously there is a viscosity term in front of it, so there is a nu term in front of it over here. Okay? यहाँ पे nu है, there is nu here. Okay? So if I from here, what I will be getting is something like a ratio of delta naught by L, and it's something similar to square root of the 1 over square root of the Reynolds number. So very simply, your boundary layer thickness, if someone asks you what is the boundary layer thickness in this Reynolds number, it is just take the square root of the Reynolds number, inverse it, and that might be a very approximate but a bad value, but it's a good starting point to begin with. Okay? So delta naught is that. But we have not still reduced down to the lubrication equation. So one thing we can see is that we know that the strength of del 2u by del x squared is very small, so that is dead. Okay? Now, if you look at the momentum equation in the y direction, we'll do the same operation. U infinity, we'll put u is equal to u infinity v by x, that is L. We substitute the value of v and we'll get something like this. Okay? We substitute the value of this. The same thing goes with the v dv by dy. You'll get something like that, and you'll find that both of them are nearly the same, which is great. And what you'll find is, if you do the same operation in the y momentum equation, you will actually find something like u infinity squared by delta naught by L cubed. There is an L square term, and as I mentioned, L is much larger than delta naught. L squared would be even larger, L cubed will be far larger. So that means these guys are almost becoming 0. So you can see that the viscous terms in the v direction are immaterial, are becoming small in significance. Okay? And the same is true with the inertial term. Inertial terms, they've got the denominator as L squared, so both of these are also dead. So essentially, what you will have is the y momentum equation is basically something like 1 over rho del p by del y equal to 0. So this is del p by del y equal to 0. That is your reduced y momentum equation in the lubrication layer, in the small layer. Okay? So basically, here you can say that, again, the meaning of del p by del y equal to 0 is mean that pressure is constant with respect to y. That means the pressure drop is only in the x direction. It has no implication in the y direction, in the boundary layer. Okay? So basically, if you look at this, you will have a reduced set of equations. So you'll have the continuity equation, which is mass balance, which will be there. Okay? And then you hardly have your y momentum equation, you just have your x momentum equation in this term. So this is lubrication equations. These are the lubrication equations. So these are reduced lubrication equations which we use for films, which we use for boundary layers. Of course, the boundary conditions would be very different in all these cases. But essentially what I wanted to talk about was how do you obtain lubrication equations. Now what we actually do is when you consider thin films or droplets and you're considering the stability of droplets, rather than starting from Navier-Stokes equation, we start from lubrication equations. So you can combine lubrication equations with stability analysis because the system is so thin that we can live with it. Okay? So with this, I would like to stop the lecture. Any questions, please? Yeah. So that's a good question. So basically, when we consider evaporating systems or base state which is not constant, there are two methods we use. One uses severe assumptions. The first assumption we make, this is called as a quasi-steady state stability analysis. We freeze the system in time. So we do the simulation, we freeze it each time. That assumes that the rate of evaporation is so slow that it is slower than the time scale of the instability. So at each frozen state, we'll do a stability analysis. So that's a much more intricate, it's a time consuming process, but we can get answers. And for slow evaporating systems, that's fine. But if you have a fast evaporating system, that goes out of the window. So for that, we use a transient growth. That's a different method. I'm going to show that to you as well. Yeah.
So that particular case, you did the experiment also, right?
Yes.
And you said, how did you suppress the instability? You mentioned something like that while in passing.
Yeah. So what we noticed is that if you, so you mean those hydrothermal waves? Okay. So one way you can suppress the hydrothermal waves is just by altering the system parameters. So Prandtl number is typically used. Prandtl number again is a property of the liquid. Okay. The other way is basically looking at thermal monogamy. So if you suppress the if your substrate temperature is not at a higher, if it is I think it's about, I remember that if it is not as warm, then you actually suppress the instabilities and you will just have very slow evaporation without any instabilities. So I think in case of methanol, I think we saw that if the substrate temperature was about 15 degrees, we must look at the paper, but is less than 15 degrees, you won't see much of these instabilities. But then if you have these instabilities, it helps because you actually make the system more efficient. But again, because of these instabilities, they can leave patterns behind as they dry. Okay? So in some cases, when you do etching of the surfaces, we would want these instabilities to happen, in fact, in a much more pronounced way. Good.